Hello YouTube community. Today I would like to talk about AI, artificial intelligence, and more specifically, computers. The question is always asked, do computers think? How do they think? And is it similar to human thinking or radically different? In October 2024, two scientists, John J. Hopfield and Geoffrey E. Hinton, were announced as the laureates of the Nobel Prize for Physics in their pioneering work on neural network research, or AI. Geoffrey Hinton is famous for also warning humanity that, quote, machines could take over the world. I think we're at a kind of bifurcation point in history where in the next few years we need to figure out if there's a way to deal with that threat, Hinton said in an interview. Personally, I think that this is hype that will not be achieved anytime soon. But on the other hand, other smarter scientists than me have also made similar arguments. As Stephen Hawking put it before he died, quote, whereas the short-term impact of AI depends on who controls it, the long-term impact depends on whether it can be controlled at all. I suppose time will tell what happens with AI. Is it hype or existential threat waiting around the corner to trounce on humanity? In this video, I would like to focus on the similarities and differences between the way that wet brains and electronic machines think. I use the term, in quotes, think loosely here. We all know that living, conscious humans think, but do electronic machines think? I know that what electronic machines currently do is more accurately described as compute, but who knows, maybe in the future they too will think like humans. And I would guess that if machines ever think like us humans, the future is very, very far away, at least hundreds of years away. If Mother Nature can create animals with wet brains that think and are conscious, then if those same wet brains put their mind to it, I'm sure they might be able to create electronic machines that think. But like I said, I think it's a very, very difficult task, and it's very, very far away. Like, it's not a matter of 5 or 10 years away. It's more like 100 or 200 years away. But that's just my 2 cents. I'm assuming that all humans watching this video are conscious and thinking. As they watch, they wonder if they should stay and watch more of this video or click away and do something else. Human minds, or as I call them, wet brains, are always thinking as long as the person is alive, awake, and conscious. Even when we sleep, our minds are thinking, replaying the previous day's activities and always imagining other realities. Now, I'd like to just get into a little bit about definitions. So at a minimum, I would define a conscious wet brain as something that helps its owner to survive, at least long enough to procreate, and maybe assist its progeny by passing on what it knows, thereby teaching it to survive. A computer, on the other hand, has 3 main characteristics or attributes. 1, it has to do mathematical computations. 2, it has to be quick. And 3, the math has to be accurate. If it cannot do all 3, then I don't see why anyone would build it, and why would anyone buy it. On the other hand, this reminds me of an actual event back in the 1990s. Windows 3.1 came out in the early 1990s, but there was a bug. If you used the built-in calculator and subtracted 3.1 from 3.11, the answer was 0. This embarrassing mistake was quickly patched. I would assume that most humans watching this video know about numbers and basic math, addition, subtraction, multiplication, and division, especially small numbers under 101. In this short video, I will not discuss all the ways humans think, but in order to make the comparison with electronic machines, I will focus on numbers and math, and one unique feature of electronic computations. Obviously, we know there are numbers between 0 and infinity, or between minus infinity and positive infinity. But what are the most basic numbers that we humans think in? I would suggest that most people have a basic knowledge of numbers on 3 levels. The numbers between 1 to 10, the numbers between 1 to 100, and then all the rest of the numbers over 100, positive, negative, fractions, real, imaginary, etc. Humans go through stages of learning about numbers. As young children, we learn about numbers by counting 1 to 10 on our fingers, and then by doing simple math like 3 fingers minus 1 finger, and then 3 apples minus 1 apple, etc. And then the complete abstraction, 3 minus 1, etc. And then as we progress, we memorize the times tables from 1 times 1 to 10 times 10. I would venture that most people that have gone through school still have in their memory cells the times tables up to 10, and some people up to 12 or higher. Anything above that, we tend to use a calculator. Beside the current decimal system of numbers, we also know of the Roman system of numbers. I think their system was similar to counting using our fingers and using our eyes to quickly see numbers 1 to 3. Actually, for the numbers between 1 and 100, the Roman system had 5 symbols. I equals 1, V equals 5, X equals 10, L equals 50, C equals 100, etc. All the other numbers between 1 and 100 are a combination of these 5 symbols. This system of numbers relies on the fact that humans can see up to 3 items without actually counting them. When we see 3, we know right away it is 3, which is why the Roman number 4 is not 4 I's, but instead IV, and 8 is VIII. You can do an interesting experiment. Throw a small number of objects randomly on the floor. If it's a small number between 1 and 4, you can probably figure it out without counting. Anything more, you will have to count them one at a time. But what about a computer? You can program it to recognize various patterns, but it will have to count them one at a time, even if it's only, say, 2 or 3 random items. So to summarize, here's a chart of the numbers that I've covered so far. Primitive numbers for humans. First we don't have 0, we have nothing. So like, you don't say, I have 0 cars, you say, I don't have a car, right? So nothing as opposed to 0. The numbers 1, 2, 3, like, so you can say, I have 1 wife, I have 2 children, I have 3 grandparents. So those are the numbers, 1, 2, 3, where you don't have to literally count them, but as soon as you see 3, you know there are 3. And then anything above 3 is a lot. Nothing, 1, 2, 3, and a lot. The advanced numbers for the Romans, like I said, up to 100 is I, V, X, L, and C. Okay, so then the advanced Arabic numbers for humans, these are the numbers that most of the world uses, the digits, decimal system, the digits 0 through 9. Now, as far as computers go, so most computers now, obviously, we all know, use the binary numbers, 0 and 1. And recently I've been reading up about the ternary base 3 numbers. Following the binary, you would think it would be 0, 1, 2, but apparently the best system for the base 3 number system is -1, 0, +1. And then there's the mysterious quantum number systems, which they have both a 0 and a 1 at the same time. So this isn't about quantum computers. I'm just gonna skip that for now. Okay, so that's a summary of the number systems and the difference between what humans see numbers and how computers see numbers. Now let's talk about modern computers and their system of binary numbers. When I was first learning about binary, I thought it would be the numbers 1 and 2, but I was wrong. Binary numbers have 0 or nothing and 1 or an electronic pulse. As opposed to human children who learn about numbers using their 10 fingers. All computers today know numbers as one category, all numbers. And they're given instructions on how to convert numbers to binary, store them, do mathematical calculations, reconvert back to decimal, and display them for human edification. Computers don't do anything until they are turned on, i.e. have an electrical input. When turned on, they go through a boot up process by reading the BIOS, configuring the basic input-output hardware. Then the operating system takes over and it waits for human input to do some task. For example, a person might open a browser and check the weather in their location, or get their email and then start the day doing their usual job. From this, we can tell that a computer is told what to do by the software and by the human that is clicking the mouse or the keys on the keyboard. Part 2. A human can observe the world around them and consider what is to be done next. Sometimes this could be a daily routine, like putting on your clothes, having a coffee, and going to school or to work, etc. Or it could be something more complex, like driving a car to work, or going to a polling station to vote for your favorite candidate. A computer, on the other hand, has an internal clock which tells the CPU to get the next instruction and execute it. In modern computers, this clock runs very fast. For example, a 2.5 gigahertz processor completes a cycle 2.5 billion times per second. Like I said, electronic computers are very fast and getting faster every year. A human wet brain, as far as we know, does not have a built-in clock. It might have a sense of late or early depending on the time of day and whether the person is tired or hungry or thirsty, etc. But as far as a clock that tells the brain to get the next instruction, no, we don't have that. Human brains can juggle many ideas and be conscious of many ideas and memories at once, but generally the person tends to execute one task at a time, sometimes two, like walking and chewing gum. In summary, electronic computers have internal clocks telling them to get the next instruction. Humans don't have this type of internal clock. Now, let's talk about math. Now I want to compare mathematical calculations between humans and computers. As I said, humans tend to think of numbers in three categories: nothing, 1, 2, 3, and a lot. If we ask a human what is 3 plus 5 or what is 6 times 7, most humans can give the correct answer, in most cases, simply by recalling from their memory. And anything over 100, they will probably use a calculator. I should add that humans are not always reliable here. Sometimes people might have an incentive to lie or pretend. One is always taking a risk when asking a human such a question. But when it comes to computers, any mathematical question must be answered quickly and correctly. If it is not quick or it is wrong, I don't see the purpose of such a computer. Now let's take an actual example. Say the square root of a number over 1,000, say 1,358. Most humans that have gone through the public school system know the method for calculating square roots. And if we do it correctly, it might take a few minutes, but eventually we should get 36.85 with a bunch of numbers after that. Now let's look at a computer. Once you open the calculator program and enter this, square root of 1,358, the computer is hardwired to do the math correctly and quickly. It reads the number, converts it to binary, 10101001110, and stores it in a location or an address. For example, register EAX. Then it sends this binary number to the arithmetic logic unit, the ALU. It does its square root calculation and returns the answer to a special answer register. Then the computer converts the answer back to decimal and displays 36.85, 105, 1545 for the human to see. I hope that viewers can see the big difference between human mathematical and computer mathematical computations. And I just want to give one more example between human and computer processes: the ability to see and understand. Both humans and computers can see, but the difference is that a human mind interprets what it sees, whereas a computer sees pixels, zeros and ones, arranged in rows and columns. Let's take this simple example. I will use a few toothpicks and lay them out on top of my stove. You can tell me what you think it is. To a computer, it probably just looks like a random number of toothpicks, but I would hazard a guess that most humans see a table, or most humans see these toothpicks laid out in such a way that it reminds them of a table. Another interesting experiment: we teach our children to get along with our pets, cats and dogs, in real time, whereas we train computers by showing them pictures of cats and dogs. And this is a very basic difference. Children learn about their environment, like cats and dogs, or their siblings, their parents. At the same time, they'll learn about the ever-present gravity. Computers never learn about gravity. Even though they might be able to quote Newton's laws of motion, they have no understanding of gravity or the fact that things cannot occupy the same space. So I'm just going to end with showing the summary in chart form. And that's it for now. See you in my next video.